In this lesson, we're going to take a look at the evaluating of logarithms. So in doing that, we've got some examples that we're going to be taking a look at down here. We've already seen the process of converting between logarithmic and exponential form. What we want to do is we want to look at a logarithmic expression, not an equation, there's no equal sign, just a logarithmic expression, and actually find the true value of that expression. Okay, now we're going to illustrate how we do this, taking a look at what this equals. So we have the log base 3 of 27. I want to know what it equals. I want to know the value of that. Okay. Well, it equals something. Because it equals something that we don't know, we'll just call that something x. Now, if we do a quick conversion from log form to exponential form, it ends up giving us 27 equals 3 to the x. The reason I did this is to illustrate that when you're back at just log base 3 of 27, what you're really being asked is, what is the exponent value that I can raise my base to that equals what I'm taking the log of? So the question is, 3 to what power is equal to 27? Well, 3 times 3 is 9, times 3 is 27. So how many 3's did I need? I needed 3 3's. 3 to the third power is 27. Therefore, the log base 3 of 27 is 3. Okay. Skipping all of that intermediate work, we can take a look at this next example here. Log base 4 of 256. All we need to do is ask ourselves, 4 to what power? 4 to what power is equal to 256? Well, 4 times 4 is 16, times 4 is 64, times another 4 is 256. So it takes 4 4's to equal 256. Therefore, 4 to what power is 256? 4 to the fourth power. So the log base 4 of 256 is 4. Okay. Now we may try another example really quick before we get to two other unique cases. Let's try this example over here. Let's try log base 2 of 16. Log base 2 of 16. The question is, what value does the log base 2 of 16 equal? Well, 2 to what power is 16? So we can say 2 times 2 is 4, times 2 is 8, times 2 is 16. So it took 4 2's multiplied together to equal 16. Therefore, the log base 2 of 16 is 4, because that's the exponent that I have to raise the power of 2 to in order to get 16. Good. Let's look at two more examples really quick. Next example here, we have the log base 3 of 1 over 81. This one is unique because it is a rational number where the number that makes sense to find 3 to the power equaling is in the denominator. So what we can do is we can focus on that denominator of 81. 3 to what power is equal to 81? Well, 3 times 3 is 9, times 3 is 27, times 3 is equal to 81. So it takes 4 3's in order to multiply together and equal 81. Now, here's the thing. What do you do to an exponent value? So right now, the x value here would be 4. But what could I do to that exponent value to take the 81 and move it to the denominator? Well, what I can do is I can make the exponent value negative, because 3 to the negative fourth is 1 over 3 to the positive fourth, thus giving you 1 over 81. So that exponent power that gives us 1 over 81 is not a 4. The 4 gives us 81, but the exponent of negative 4 gives us 1 over 81. So we now know that the log base 3 of 1 over 81 is negative 4. Lastly, in this we have the log base 5 of 125. Here's what's interesting about this. It is impossible to take the logarithm of a negative number if the base value is positive. Because if we're asking ourselves 5 to what power equals negative 125, well, nothing. Because if I take 5 times 5, it's going to be a positive number. Times another 5 is a positive number. I'm never going to get a negative number. Therefore, this is impossible to do. We call this undefined. So if you try to take the log of a negative number where the base value is positive, it is undefined. Okay, well, these problems that we looked at worked out really nicely for us. They were clean. They were the solutions were nice whole numbers. What if that's not the case? What if that's not the case? Let's take a look at these 3 examples. Okay, these 3 examples right here involve logarithms where the solutions are not nice, easy whole numbers. First one is we have a log of 65. Now there's no base value here, so we know that the base value is actually 10. Well, over here on our calculator, you can see next to the number 7, we have a log button. And again, that log right there, if I hit that button, you'll notice it does log with parentheses. It doesn't have a base value listed either. Therefore, it's a common logarithm just like we have here. So all I need to do is type in log of 65, close that parenthesis, hit enter, and you end up with this equaling 1.81. Now, next example here does have a base value. The problem is in our calculator, the log button alone is a log base 10. We have a log base 3. So here's how we do it. We hit our log button. We're taking the log of 38. So I'm going to hit 38. I'm going to type in 38. And then right above my 7 is my comma. I'm going to hit the comma button. And then what I'm going to do is I'm going to type in whatever my base value is. Well, my base value is 3. So I'm taking the log of 38, comma, with a base value of 3. Close that off, hit enter, and it gives me 3.31. You'll notice if I just did log of 38, it would have given me a different answer because it was using a base value of 10 rather than a base value of 3 like we have listed. This last example, the natural log of 6.32 is a little bit more unique because we have a natural log instead of a logarithm. Fortunately, right under the log button on our calculator, we have a natural log button. So it's as simple as doing the natural log of 6.32. Closing the parenthesis. I don't need to do comma base value because natural log is already natural log, log base e. Hit enter, and that gives me a 1.84. Okay, so you can see that you can do logarithms by hand in your head sometimes because the numbers work out nicely, and in other cases like the 3 we just did, it doesn't work out really nice, so we end up having to use our calculator to evaluate the logarithmic expressions to find the true value of the logarithmic expressions.